Okay, last time I spoke a little bit about these crazy wormholes that could exist. They're absolutely crazy. If they exist at all, they would be a wormhole related to a black hole. That is to say, you could fall into a black hole, and you can't get back, but you get down into the center. The usual way we think of it is you get crushed, and you aren't going to survive at all. But there are some possibilities that you exit through the black hole. You just keep going. You fall in here, and maybe you would come out the other place, someplace weird. That's a conjecture that's probably completely wrong. But nevertheless, it opens the door for lots of science fiction stories and, Star Trek episodes. Nevertheless, the reason this is allowed is that all this is possible within differential geometry. Einstein's theory of relativity made heavy use of differential geometry, but it didn't talk about this type of object. Scientists don't really think they exist, but it's hard to prove it one way or another. Okay, so maybe you could, if you found one, you could just go over to it, drop in, and end up a shortcut to Vega instead of taking 25 light years to get there, or 25 years times the amount you're slower than the speed of light. You could maybe make it quicker. Well, that's crazy. All right, so and this is not completely impossible, but nearly impossible. So we're going to see evidence for massive black holes in a little while. There's evidence for a 1 million solar mass black hole in the center of our galaxy, and I'll show you that evidence. In fact, you're going to prove it. And it's pretty astounding. There's evidence for billion solar mass black holes in other galaxies. How did they get there? That'll be a question we will ask. Okay. So that'd be nice if we could use them as shortcuts to go someplace, but it's not likely to work. But that's why they're made up. They're not impossible to have within differential geometry. Although differential geometry, as Einstein imagined it, did not have them. Okay, so until we prove they don't exist, you can write all the science fiction stories you want. Even if they do prove it, it doesn't matter. But a lot of the best science fiction writers these days try to take cognizance of the limitations of everything. They take cognizance of the limitations of special relativity. And they can go fast, but they don't tell you how to do it. But special relativity limits you, and your age gets long. There's a book I read about called The Forever War by Joseph Haldeman, in which humans are fighting alien race, and they go off and fight battles, but the battles turn out to be 1,000 light years distant. Now, it only takes a year to get there, but it's 1,000 light years have passed, and they come back to the Earth several thousand years in the future. And so what do they do? It's very interesting, but I don't think it's too realistic. All right, so the important thing to note is about relativity, that it was a failure of Newtonian mechanics. Newtonian mechanics was not the final word. And Newtonian mechanics had remember that was written in a time when nobody knew anything about light. They certainly didn't know about speeds approaching c. And the special relativistic effects only come in when you are moving at speeds close to the speed of light. Similarly, the potentials were never so strong that this basically means that the potential has such an escape velocity that it exceeds the speed of light. And can you imagine? The Earth has an escape velocity of 10 kilometers a second. Very, very small compared to the speed of light. Can you imagine the Earth getting so dense that the escape velocity is the speed of light? Well, that's what it's talking about. So, all right. So, Newtonian mechanics works perfectly well. Mechanics slowed down. It failed gradually, and that's a good theory. It fails gradually. The same is true of quantum mechanics for classical mechanics. Classical mechanics is perfectly fine. Okay. Now, the issue of black holes, the universe, there are various conjectures about what happened in the universe. One suggestion that has been made is probably not right, or is pretty surely wrong, is that the black hole formed tons and tons of, the universe, when it was young, formed millions of black holes, each weighing about a mountain, about Mount Everest. Okay, and they were really small. They're smaller. They're so small, about the smallness of a wavelength. A micron. Now, that's going to be a very dense object. So it probably doesn't exist, but there was thought that they existed, and there was thought that you could see them. Something was producing something that people thought was possibly a primordial black hole, as they're called. But that turns out to be wrong. Okay. Now, today, I wanted to speak about physics that is really necessary to understand, at least roughly, the idea. So, because we're going to use this quite a bit in the course. All right, this is particle physics. And this is an event that took place in a particle. And it took place here, and it sent off a jet of stuff here, another jet here, and a little bit there, and a little bit here. I don't know what any of these tracks are, but physicists look at this, and they try to understand what's going on. Basically, they take particles running one way to hit on into particles running the other way, and they try to understand what happens when the collision of particles occurs. That's about the only way you can get the particles up to incredibly high energy for exploration. But the problem is that it's equivalent to throwing two watches together. If you throw a watch and hits another watch and splatters all over the room, you see little pieces of the watch come out in various places, and you try to figure out what's inside the watch. That's not very promising, but that is all they can do. So they slam together these particles, and they can be complicated, and it's very difficult to understand them. But nevertheless, they try it. Now, remember quantum mechanics, which you learned in chemistry course. Did you all learn a little bit about quantum mechanics in chemistry? Shaking your head, no. No. Yes. Who says yes? Raise your hand. All right. Well, quantum mechanics is a law that governs the motion of an atom, and smaller. And it was worked out in first starting with Max Planck, who was a scientist, a German, and there's a new constant in the world. This is a constant little h. It's known as Planck's constant. It's a tiny little number, and its use is the following: the energy of a photon is h times nu. Nu is the frequency, cycles per second, and that is conjectured. It was not conjectured. It was first posited by Einstein, and he needed a constant, and Planck, they just called it Planck's constant. Okay, now this is part of the particle nature of light. Remember Einstein talked about this photoelectric effect. Just wait a second. Has anybody seen the lectures on B-space? Okay. Sorry? It's not? Well, not yet. I'm just giving it. I mean, no. This lecture will be on B-space sometime. I don't know. But it's just it has my voice and it has the screen. It doesn't have a video camera of us. So, okay, that's kind of neat. All right. So the photoelectric effect is what Einstein won his Nobel Prize for. And this is when you shine a light at a metal. If the light's of a high enough frequency, that is, the photons have enough energy, they will hit the metal and knock an electron out of the metal, and that is called photoelectric effect for obvious reasons. Okay? Electrons jump, they'll actually jump off the surface. Now, the minimum energy, I said, depends on the frequency. It does not depend on the intensity of the light. And that is saying that it's really one particle interacting with the metal that does it. If you can have the photons come in every minute, and it will still happen. Okay. Now, minimum frequency, no electrons ejected. So this is a proof that the photoelectric effect has to do with particles in the atom. Okay, so this is what Einstein proposed. He is the one who proposed this equation. All right, momentum is like ordinary mass. Momentum of a particle is when you get hit by an atom or hit by your friend, he imparts momentum to you. He bangs into you. And he imparts a little momentum. It turns out to be, technically, it's the mass, his mass times his velocity is the momentum. Photons have momentum too. Even though they have no mass, they have momentum. And Einstein showed that the momentum is called P, and the P was equal to the energy divided by the speed of light. Doesn't really matter what it is. I'm never going to ask you to do something with it, so don't worry. But this showed that photons carry momentum, and this is something important for what we'll see in stars in a little bit. So I'm just giving you a little bit of preview. Okay, this explains what's going on, and etc. So this is the usual question: how can a photon be both a wave and a particle? It's a fundamental question. How does it do it? And Einstein he would not accept that photons have uncertainty in them. He understood the necessity for them to be particles, but he never understood them to be uncertain, as we'll see a little later. Now, de Broglie, he tried to understand what's going on with these atoms as well. He was another famous physicist. Rutherford did very important experiments. I don't know if now, in the old days, they didn't know the structure of an atom. They didn't know that atoms contained heavy nuclei in the center and electrons on the outside. That was unknown. Now, have you ever heard of the Rutherford experiment? Okay, the Rutherford experiment was such that you shot, say, a little particle, say a neutron or a proton, at a sheet of gold, real thin piece of gold. Now, if the electron consists, if the gold consists of swarms of electrons in the center and protons all swarming around, the particle which came in has enough energy, it'll be just deflected a little bit. Okay, it never gets a major deflection. But Rutherford observed that that was mostly what happened, but once in a while he saw a huge bounce. It came back at him. So here's the idea. Here's a piece of gold. What's gold? What's the word for gold? AU? AU? In a thin sheet. And you send particles at it, and most of them just go through. But once in a while, a particle gets bounced here or here. And Rutherford said, well, how can that happen? How can the particle be bounced? And this is a proof that the only way you could do it is if you put all the mass of the atom in the center in its nucleus. So he showed that nuclei existed in atoms. We did not have any proof of nuclei's existence, and this was in the 30s. And this was an important concept. Okay, so that gives us the picture that you have of the atom. That is, it has a swarm of electrons around a dense nucleus of the protons and neutrons. Explaining that was a complicated business. And okay. All right, so, and the question is, why doesn't the atom emit all the time? Now, the problem is that if you have a particle moving in a circle, all right, the particle moving in a circle is like the Earth moving in a circle around the sun. The Earth is being accelerated by the sun because it's not moving in a straight line. If you move in a bent line, a circular line, you have to be accelerated continuously. The acceleration of the atom turns out to make the atom, this is pretty much the same problem as the Kepler problem. The atom exists. Think of the electrons as circling. If circular orbits obtained, there's a force that makes the thing in a circular fashion. You don't have to know any of this, and you're not going to be expected to realize it, to remember it, so don't write notes. Please. All right. There has to be a relationship between the velocity of the atom and the distance of the electron. The velocity of the electron and the distance of the electron from the nucleus. Very similar to gravity. And scientists recognized that electrons are in continuous orbit as they circle the atom. And so the question was, well, if it's in continuous orbit, why doesn't it radiate? Because that is exactly the radiation requirement. A particle zooming around, if it's zooming around, it radiates energy. And if it does that, why does it still maintain itself? As electron loses the energy in a classical way of computing, it'll spiral into the nucleus. And it should be unstable. According to their thought, the classical atom is unstable, and it should decay in less than a microsecond. Now, that's obviously ridiculous. Atoms are not unstable. They don't decay at all. And explaining why they don't decay was the fundamental problem the physicists realized in the early part of the 20th century. All right. Atoms don't do it. All right, so now they started to, they really were puzzled by this. This was a serious problem. And the first analysis of this was by Niels Bohr. Who's heard of Niels Bohr? Okay, that side's heard of it. Nobody on this side has heard of Niels. Okay, so Niels Bohr was a very famous. He was Danish, and he made up the first theory of atoms. That his theory made some sense, but it doesn't actually work very well, and it's not really right, but it is what you learned in chemistry because it allows us to make pretty pictures. Okay, so he said, all right, let's consider the motion. All right. If you consider the object, you consider it waving just a little bit. It waves a little bit like this, and if it's going to wave in a few times as it goes around the orbit, then there's a quantized orbit's phase. If the orbit is too long, it won't fit a number of waves. The number of waves that you can fit in there will not be an integral number of waves. It can't be 1, 2, or 3. It'll be 3.5. And he said, no, that's not allowed. Let's just say that that's not allowed. He doesn't know why. He just says, okay, that's not allowed. And so he's going to count the waves. He's going to count them by n, the principal quantum number. All right. So he gets, he divides it into this object, and you get principal quantum numbers out of it. And you solve the circular velocity of where it is. The different n's put you at different orbits from the sun, from the nucleus. You solve for the velocity. The velocity is equal to this. Don't worry about what this is actually equal to. And this tells you that the radius of this atom is related. Here you can put in what you know for velocity, put in all this other stuff, and it goes to this level. And basically you can determine the radius of the atom. Well, that's what he said was a model that'll work for the internal structure of an atom. Please don't copy down the math. I'm not going to hold you responsible for it. All right, so what do you get? All right, basically he said that the transition from one state to another is given by the principal quantum numbers 1 over n squared. Okay, and you start drawing atoms in this sort of energy level. Have you seen this before? All right, this allows you to draw the atoms and the energy levels they take. This is all from the Bohr atom. This is not quite correct, but it allows you to do it. All right, so you could have transitions of a certain wavelength, a certain energy, more energy, et cetera, et cetera. And it's all governed by this quantum numbers. All right, it works, and it works for hydrogen. It doesn't work for anything else. The model's too simple-minded. It's okay. It's progress on the theory of the atoms. And the theory of the atoms has quantum mechanics in it. People didn't understand why. Okay, so the quantum madness continued. People, Heisenberg and Schrodinger, they finally provided mathematics that worked. Now you've heard about the uncertainty principle. Okay, that's known as the Heisenberg uncertainty principle. All right, And all right, and they've realized that everything in the atom is specified by its so-called quantum numbers. Okay. The quantum numbers turn out to be, they must tell us what the internal degrees of freedom are in the atom. So there's a quantum number n, the principal quantum number from the Bohr atom. There are quantum numbers L and M. They label the angular momentum and the orientation of the angular momentum. These are certain rules. And there's something called the spin angular momentum, which has half integer. And the spin can be up or down. Okay. All right, so that's, be it as it may, this is what was necessary to explain an atom, any atom. All right, and so eventually people understood what was going on. This is what Einstein never believed, that there was an uncertainty of uncertainty in the momentum times the uncertainty in the position was always greater than some constant h over 2 pi. It's just greater than that. So that means if I localize the atom to extremely precise level, then the uncertainty in the momentum is a little larger. And the product of them has to be greater than h over 2 pi. Now, these concepts are used in astrophysics. And so I'm telling you how this works. It's a little bit. I'm not going to explain precisely, but astrophysics makes use of this. Well, white dwarfs, neutron stars make use of the effect. So we have to understand it a little bit. Okay, the atom we now understand, the electron in a nucleus. The electron is not really described as moving around in a nice particle. It is more like a smear of cloud of where the electron is. And in excited state, it's a little bigger. Ionization it eventually rejects an electron from the atom. Okay, so then this is the one that really matters. Pauli, Wolfgang Pauli, again a German physicist, he talked about the quantum mechanics of photons and particles and electrons and protons. And what kind of quantum mechanics do they have? All right. First of all, he calls them, well, we now call them bosons and fermions. Two types of particles in the universe. Bosons are things like photons. And it turns out they have an even number for they have integer number for S is 1, 2, or 3, and that makes it a boson. S equals a half or 3/2 makes it a fermion. Now, this is all very technical and not very useful to you, but we'll see what it means in just a minute. This is what physicists realized in the 30s and 40s and 50s. They made up these terms, and that told them what it did. Now, what does it mean to be antisocial? Antisocial meant that you can't have two of them in the same state. The state is occupied if everything is put there. Everything is there. And for some reason, the electron being a type of fermion, the electron cannot be in the same state as another electron. And that is very, very important for neutron stars and white dwarfs. Okay. If its lowest energy states are occupied, if you have, say, an atom with 6 electrons in it, it's a ground state. It's carbon, and the carbon electrons have different states, but there are always the lowest energy states that are possible. I mean, that's what the ground state of carbon is. Okay. So this is the picture you saw. The atom has 2 electrons in the internal state, and the third electron, it cannot be in its internal state because you have one spinning up, another spinning down for up and down. For 1/2, one's up, one's down. You can't have 3 of them. So the third electron has to be in another energy state. All right, and that seems to be a requirement of the Pauli exclusion principle. Why this is necessary was understood in the 50s. All right, it's very complicated to understand it. All right, this is how atomic structure is explained and how white dwarfs are explained. And white dwarfs are a condensed matter of is what our sun will eventually turn into in 5 billion years, white dwarf. And I'll tell you about that in a week or so. All right, so the energy, if you have an energy, the positron or an electron can convert totally its rest mass. Electron weighs something, positron weighs something. A positron is the opposite of an electron. If they should come together, they will turn totally into photons. So what you have here is a situation that doesn't conserve mass. There's a lot of mass on the left-hand side, no mass on the right-hand side. That's okay. There's no law about conservation of mass. The law is conservation of energy. That is conserved. The energy of the positron and electron is exactly equal to the energy of the photons. Similarly, the photons can come together and annihilate and produce a positron and electron. That is possible because of the conservation of energy. If the energy is sufficient to make a positron and electron, it'll do it. Okay, now here's another factor you learned. That there's something called quantum tunneling. This is a process that the sun uses. You can sit in a jail. If you're an electron, you sit in a jail, and every once in a while, you're out of the jail. What the hell? What's going on? What we're saying is the following. Okay, suppose this is energy. This is the energy equals 0, ground state, and there is a state like this where electron is trapped. Here's an electron, and it goes back and forth. Okay. And it can't get out of this because the energy is such that it doesn't have the energy to do it. This is drawn wrong. Suppose this is the energy. Okay, and this is energy equals 0. Now, if the electron could leak out of this box, it would then be free and would be able to escape the vicinity, and it would fly away. Now, it turns out that in a nucleus of an atom, when you're trying to bang together hydrogen to make it into helium, that the situation is about like this. that the particle in here, if it gets in here, it's okay. But if the particle is here, it can leak out slowly, very slowly. And that's just like the man who's trapped in jail. He gets out. And this is all possible in quantum mechanics. Crazy, but it can be done. And this process is necessary for the explaining what goes on around nuclei. And we will talk about this as we get to it. Okay. Now, this is incredible. To do all this in the early part of the 20th century was an amazing achievement. It was all before my time, before your time, obviously. And it showed that the rules of quantum mechanics govern everything that goes on in smaller scales. That means all of the elementary particles. And it plays, these are the roles. This is critical. Understanding a little bit of quantum mechanics is critical to understand how the sun generates energy, how all the elements are made in the centers of stars, the structure of so-called degenerate stars, like white dwarfs and neutron stars. It turns out they have a maximum mass, and this is all given by quantum mechanics. Generation. So here's four issues. Finally, the generation of all the seed fluctuations that make the structure of the universe is all due to quantum mechanics. So this theory, you may think, doesn't have much application. It turns out to be essential for governing the universe. So the universe depends on gravity, a force that applies at very, very big scales, and also depends critically on the quantum mechanics, which is a force that applies on very small scales. So you have to understand just roughly a little bit about quantum mechanics. Now, not knowing anything about quantum mechanics, there was a famous physicist in the 19th century. Who was the physicist, Eric? The 19th century physicist who told what the age of the Earth was, or age of the sun was. Got 50 million years. Who was the physicist who told people the age of the sun can't be more than 50 million years? Kelvin, yes, Kelvin. Age of the sun. Now, this physicist estimated, he went through and did some estimates and said, the sun is only 50 million years old, and the geologists said, no, that's wrong. It's we're sure it's about 4 billion years old. They knew this at that time. And Kelvin said, well, that's what I calculate, 50 billion years. Kelvin at the time, this was in the 19th century, Kelvin didn't know any of this quantum mechanics. This was all invented later. He was gone. And the quantum mechanics is the sun's generator. Kelvin was assuming, well, he made the sun's energy come from the sun shrinking as it cooled off, which is not how it works. You don't live very long in that case. But if you're going to explain the sun's brightness and its history and everything about the sun, you have to know something about quantum mechanics. Okay. Now, there's something else that these quantum systems do, and that's pretty incredible. If you heat a balloon, like here, we heat a balloon with this candle, and the gas pressure goes up, the temperature in the center of the balloon goes up, and the balloon expands. It expands because the gas pressure is higher. It's hitting on the side of the balloon and making the balloon expand. All right? Now, and what it is dominated by is the thermal pressure. The thermal pressure is the pressure of anything, anything that you're used to. Okay, but there are other pressures as well. Another pressure is critically important, and we'll talk about that because we're going to use it. All right, so you heat the gas, and then you cool it down. All right, you let it gets off the flame. You put it here, put it on ice. It cools down, and continue through the cycle: heating, cooling, heating, cooling, heating, cooling. All right, and and eventually the gas becomes extremely dense. All right, now, eventually you run into the exclusion principle, the Pauli exclusion principle, which says you can't pile the electrons too tight together because they're going to have the same quantum numbers. That's not allowed. And so he says they can't get on top of each other. Okay, well, that's not allowed. And it's stopped, the compression is stopped by something called degenecy pressure. Degenecy pressure is a pretty weird name. It says the electrons are degenerate. What do we mean by degenerate? Okay, here's an example of degenecy pressure. Students come into a classroom for start of lecture. There's a lot of extra chairs, like here. You don't have trouble finding a seat. They come in and sit down, and everybody's quiet. But suppose we went in and took away these seats, and we took away 2/3 of the seats in this room. Then you'd come in, and you'd be wandering around, and you hit the walls, like this guy, hits the walls, bounces off the wall, and you exert a pressure on the wall because you can't find a home in the seat. And so you bounce and bounce and bounce, and that pressure of you hitting the wall and bouncing back is called degeneracy pressure because you couldn't fit in the seat. You're treated yourself as electrons. It's a bit fanciful. All right, musical chairs, and the chairs are quantum states, students are electrons. And so you can act like electrons in a degenerate gas, sort of. Okay? And they move faster and faster trying to find an empty seat. It's like the game of, musical chairs. As the chairs get removed, you walk faster and faster to try to get one of the few remaining chairs. Okay, and they provide, these students or electrons provide degeneracy pressure. This is really important. All right, and this is what supports gravity, supports these stars. These are known as degenerate stars, dwarfs, and brown dwarfs and white dwarfs. And well, I'll tell you what they are later. This is what holds the stars up against the force of gravity that wants to squeeze them to death. And it's held up by this so-called degeneracy pressure. It's not an issue for our sun, which is not degenerate. But eventually our sun will become a white dwarf, and then degeneracy pressure will make a big difference. Okay. And the issue is the degeneracy can be so large that the electrons can approach the speed of light. And the electrons are really pushed. You can squeeze this thing so hard that the students are bouncing off the walls and they're traveling the speed of light to do it. That's a really tight space. And as they travel faster and faster and they become degenerate and they're moving relativistic speeds, it turns out that they can't provide much pressure. The pressure of the degenerate gas is not going to work. The electrons will collapse and they will form neutrons, and then the neutron star will hold it up, and it goes on and on. It's amazing. And if these degenerate neutrons are overcome, we finally create a black hole. And these are steps on the way to making a black hole. This is how the sun can become a black hole. You have to take the sun and squeeze it and squeeze it and squeeze it, and it gets down to a size of a radius of 1.5 kilometers. How big is the sun now? Well, it's a hell of a lot bigger than 1.5 kilometers. you know, million. What is the sun? It's huge. It's almost, the radius of the Earth is 5,000 kilometers. The sun's 100 times larger, 500,000 kilometers, 1,000,000 kilometers diameter. Okay, you got to shrink it about 1,000,000 factor. And how do you do that? How in the world can I take the sun and squeeze it so hard? What in the world is going on? How does that ever happen in the universe? And believe me, it happens. And we'll talk about that as we go on and we talk about the evolution of stars. They get squeezed so hard that they're never going to get out of it. And they're trapped in a black hole or a neutron star. So we got to see how that works. Okay, then there's another thing that happens. If you have most of space, you can have these virtual particles created and annihilated in a very short time. For example, electron and positron could be created here and destroyed there. This can happen in a vacuum. It's happening all around us as we're sitting here. The vacuum has these fluctuations in it. You don't see them, nobody sees them, but it makes them nonetheless. These pairs of virtual particles. But now suppose the right next to the black hole that you do the same thing. You make virtual particles next to the black hole. And what can happen is the virtual particle can, one half of it might just wander into the black hole. The other half doesn't wander in the black hole, and you say, where'd it go? He cannot get in. This one into the black hole is stuck. He can't come out. And the other one's free. So apparently, it's going to look as though this black hole emitted photons. But black holes are characterized as emitting nothing. And yet they can somehow emit photons or positrons through this virtual emission. This then flies away and takes energy with it and causes black hole not to live forever. And this is something that was first discussed by Hawking. Stephen Hawking he was the one who understood this. And these energy this is because of quantum mechanics of the electrons and positrons in the vacuum of space. So black holes in the outer space can actually radiate slowly. Okay, so that's crazy. Now, we are trying to understand what's going on in the atom. And to do that, we are building a gigantic particle accelerator. This is an aerial photo of the gigantic accelerator between France here and Switzerland there. It's right down the middle. They're split. This is the so-called CERN facility. The particles race around this track, and positrons say antiprotons go this way, protons go this way. All right, they race around, and they are designed to collide at 4 places where storage rings, where they have facilities that can see it. There's some here, some here, some here, and here. Maybe 6 facilities. I don't know, maybe 6. Okay, now, here is what one of them looks like. This is just mind-blowing. This is a machine called Atlas. A person standing next to it will be about as big as this first pedestal here. This is a gigantic machine. This thing costs a lot of money. 3,000 physicists are working on this thing to understand what's going on. It's 46 meters long, 25 meters high, 25 meters wide. It's circular around here, and the particle collision occurs right there. So the particles come in, they collide, and then All around here are detectors that are looking for the debris of that collision. Okay, here is a picture taken from their webpage of this machine in construction. You note the guardrails here, as for a man to stand. This thing is huge, a huge machine. Berkeley physicists are participating in the machine as well. This is during the construction, and this is eventually this whole area will be filled in with more and more detectors. But this thing is a gigantic machine. It is going to be operating in a year or two, and you should stay tuned. It may find important particles for us. It may find hints to tell us what the dark matter in the universe is, and we'll talk about dark matter a little later. Okay, now, as the physicists understood what was going on with the particles, it's come down to crazy. They have a zoo of elementary particles. And the zoo of elementary particles is first of all necessary to understand the structure of protons and neutrons. Now, when I was in school as a child, well, I was 15, none of this had been discovered about 40 years ago. And I learned that the elementary particles in the universe were neutrons and protons and electrons and photons and maybe something else. That's what I learned. The protons were considered an elementary particle. But now protons are not elementary particles. Elementary particle means something that cannot be subdivided further. But protons are like atoms. They can be split up. Now, have you learned any of this business in school? You learn about the divisibility of protons. Well, some of you didn't, all right? And what they know now is the protons are made of 3 quarks. Up, up, down for the proton, up, down, 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 up for the electron. For the neutron, the charge of ups are 2/3, and downs minus 1/3, and so 2/3 plus 2/3 minus 1/3 is charge 1. 2/3 minus 1/3 minus 1/3 is 0. That's the charge of a neutron. Okay, so when they put these particles together, they found that they are funny generations. The up and down quark, these are quarks, are the first family, and the other ones have crazy names, colors, strange, top and bottom. And they have leptons associated with them. Electron neutrino, an electron, and then these crazy things, muons, muon neutrino, tauon, and tauon neutrino. And finally, they realize that the photon has 3 other particles with it. Photon has the G, Z, and W bosons. These are all bosons. These are leptons. Those are quarks. They're called crazy things. All right. How does this work? What the hell is all this stuff for? Why is all this stuff in the universe? Physicists do not understand it, and they wanted to understand it the same way that that physicists have wanted to understand the universe and all of its gory mess. Now, they know the following, that the 4 forces of the universe, electromagnetic, weak, strong, and gravitational force, are all a little different. But they know that the weak force and electromagnetic force can be unified into something called electroweak theory. This is similar to the work Einstein did when he was a young man. After he won the Nobel Prize, Einstein worked and worked and worked and worked, trying to unify gravity with electromagnetism. He tried to unify them in one theory. How did he do it? Gravity, he knew, was a 4-dimensional space-time. It was a four-dimensional theory. And he said, well, let us make a fifth dimension. Let us just imagine there's a fifth dimension, and that will be the dimension of electromagnetism. And so we have five-dimensional theory, and this makes electromagnetism and gravity into one theory. It never worked. He tried and tried and tried, and he couldn't make it produce the particles of an electromagnetic field. Just didn't work. He tried. He spent about 40 years on this problem and didn't make progress on it. It was beyond he just didn't see it. Physicists are still trying. And in the 60s, 1960s, they realized how to unify electromagnetism and weak forces into something called the electroweak force. They did it. And Nobel Prizes were handed out to the people who did it. Because this is so hard, it's unbelievable. But they did it. Now, it doesn't affect us mostly. It'll affect us at the end of the course, though. So that's why I'm telling you about it. And they're pretty sure that the strong force can be unified with electroweak theory in what is called the grand unified theory. And these are, as we go to higher and higher and higher energy, we think that gravity will unify with this grand unified theory into one force, and all the forces of physics will be described by one force. But that will be extremely energetic to do that. How is that done? Well, the people who think they've got a way to do it found that no, you can't do it in 5 dimensions. You actually need 11 dimensions. In 11-dimensional space, you can unify all these forces in one. What the hell is 11-dimensional space-time? What a crazy business is that? How can that be? And at the end of the course, we will see. So stay tuned if you want to understand what that's for. We're going to come back to all this nuttiness. This is Einstein's dream. It's every physicist's dream. And they continue to work on it. It is so hard. Mathematically, it's just about impossible. Okay, now this is why they're trying to build this huge facility in CERN. It's not going to get enough energy it'll get energy that gets to this point and just a little more. They won't get energy to take the grand unified theory, because they can't do it. To get energy sufficient to grand unified theory is more energy than is available on the Earth. And the thing that's being built in CERN is about as big as anybody can imagine. You can't imagine building a project that costs more than $10 billion. You can't manage it. But that thing cost about $10 billion. That is pretty damn big. All right? And so for $10 billion, we'll get to here. And maybe we'll learn something that we can possibly extrapolate further. So that's why it's being done. Okay. That's the end of what I have to say. And that is telling you what physics will be used in the course as we go further. We are next going to talk about the sun. And the sun is a magnificent object, and it does lots of things that you probably aren't aware of. So stay tuned. By the way, has anybody worked on the lab? 2 people, 3, 4? Come on! You got to work on that lab. I gave you a lot of time because I want you to look at the sun setting over a few days. Now it's very clear, so go watch the sun. And besides, you don't want to wait till winter. Do it now. Got to look at the sun. And similarly, look at the moon on several nights in a row. So I want you, they're not hard to do. I just want you to get on with it. All right. Anybody want to know about my pump? It's right here. It's about this big. If anybody wants, I'll pull up my shirt. But the pump is injected once a month. The doctor injects a needle into the pump, which in the center, it's a big thing this big, but in the very center is a rubber grommet, and you can stick a needle through it. So she sticks a needle through it, and it's not just under the skin, doesn't hurt. And then she can inject the medicine that goes into it. And then it sits there, and every day the little pump pumps some of the medicine. It goes in a thin tube into my backbone, and it drips down from there. And its role is to get to the nerves that control my muscles, and it tells the nerves to quiet down. Don't fire too often. Just be quiet. Because if it weren't doing that, they would pull me. They'd pull everything the way this hand is pulled. They would pull it, and I'd be all a knot. I wouldn't be able to move, and I'd have to be in a wheelchair. So this is it's amazing, this stuff they have for strokes. But this is what I've got. So okay, if you want, I'll show it to you, but not out the whole class. Okay, I'll see you on Tuesday. If you here's your homework. Turn in.